Now, I should have mentioned this back when we were talking about Ampere's law. Yeah, we looked at a coil and the way we find the magnetic field inside a coil using Ampere's law. And then we simply use a path that looks like this, with this part of the path inside the coil, everything else outside. Almost all your magnetic field contribution to the line integral of the magnetic field around this is parallel to this side. And the amount of current enclosed in this loop is just the number of loops, okay? I said around this loop, and now I'm talking about these loops. This is a loop, and these things are loops. So I've got two loops here, and we're having a little trouble with language, but yeah, we're talking about the line integral of the magnetic field around the green loop, and then you have the loops of your solenoid, cylindrical solenoid. Wire wound around a cylinder. You take the number of wire loops cut through this thing, that's just the number of wire loops in this length, whatever this length is, and you could use any length. And you can figure out the charge enclosed. Once for every time the wire penetrates this green loop here, this imaginary loop in space. Okay. There's also toroidal solenoid. Now, I didn't do the toroidal solenoid in class. Your book does a good job of it. If you understand a cylindrical solenoid, you can understand the toroidal solenoid. And if you don't understand it, you're going to go grab the formula and you're going to solve the problem anyway. Better to understand it, and all we do is we wind the wire around a donut shape. And then our green loop, the loop that we're talking about here with Ampere's law, is just a loop between, well, through the inside of that donut, of that torus. And the plane, or the region enclosed by that loop, in this case the circle enclosed by that loop, is penetrated every time the wire goes through the loop. So every time the wire comes around here, it goes around the inside of the torus, it's going to penetrate this circle. So you just multiply the number of wires in the toroid by the current, and you have the current enclosed. By symmetry, and symmetry is a great big deal. You really need to think about symmetry. Just another piece of parting advice I'm giving you. Saves a lot of headaches, gives you much deeper understanding. So you want to think a lot about that. By the symmetry of the situation, the magnetic field is uniform in magnitude around this loop. It's radial. Of course, we've shown here an argument could be developed into an argument of why it's radial, but they're simply symmetry arguments give you that. And I said it's radial, and that's not right. It's tangent to this circle. Okay, it's tangent to the circle, perpendicular to the radial line. So I'm using all kinds of wrong words here. But take the idea, okay? The symmetry of this thing tells you that the magnetic field has constant magnitude, and it's always tangent to the circle. So the total line integral around here is just the diameter of the circumference of this circle multiplied by the uniform magnitude of the magnetic field. Since you know the charge enclosed, or the current enclosed, and if you know the radius of the loop, then you can easily calculate the magnetic field. And your textbook does a very good job of that, as it does with just about everything. Dearly love the textbook.